Okay. All right, so let's do an example. We're going to do that example that was here. So let's take a look at this one off the little sheet, and I put it in the lecture handouts. So this is our Spindletop example. Okay. So it says on the ride Spindletop at the amusement park Six Flags over Texas, people stood against the inner wall of a hollow vertical cylinder with a radius of 2.5 meters. The cylinder started to rotate, and when it reached the constant rotation rate of 0.60 revolutions per second, the floor on which the people were standing dropped about half a meter. The people remained pinned up against the wall. And so then we're doing a free body diagram. We're going to do a force diagram instead. Minimum coefficient of static friction. The person is to not slide down to the floor. Okay. So, so I like this example because there's a good chance y'all have actually ridden this ride. Has any of you ridden Spindletop? So this is a top-down view. Yeah, cool. Yeah, so the walls of the cylinder are like this, and it's going to rotate around like so. So I really like this example. I mean, it was a cool example. I was really sad when they like removed it from the book. You know, it's like, no, we need that one. So, and so I just went and copied it. And so they say that the radius of the cylinder is 2.5 meters. So this is going to be my person. We're looking down on the top of their head, you know, something like this. So there's a manual riding the ride. And so what this means is that when it's rotating like this, then, you know, a manual would be going around in a circle. And anything that moves in a circle must be accelerating in towards the center of the circle. So there must be a centripetal, or if you want, a radial acceleration that points horizontally in towards the center of the circle, like this. Okay. Now, keep in mind that if we're rotating this way, then the velocity will be tangent to that path of motion. And again, sometimes they'll label this as a tangential velocity, or VTAN. It's very common, okay? And I don't think we know that one yet, but we know some stuff. So what did they tell us? So I got the 2.5 meters. Oh, the 0.6 revolutions per second. Let's take a look at that. What quantity is 0.6 revolutions per second? What do we see with that? That is exactly a frequency. Wow, that's a good job. Yeah. Revolutions per second are hertz. This is the frequency. And if we remember from our chapter 3 discussion, then the frequency was the reciprocal of the period. Okay, so from this we can get the period of the motion as they go, you know, round and round. And then with our radius and the period, we can get the magnitude of this tangential velocity, you know, the speed. So let's go in and do that. So then we can go in and say that, well, this tells me that the period of the motion is 1 over 0.60. And this is an SI unit, so we'll be good. It'll come out in seconds. So it's 1.1. I guess it is, this is 6 over 10. I take the reciprocal, it's 10 over 6. 6 goes into 10 once. There you go, 6, 7. Thank you. There's our remainder bits. So now we have the period and we have the radius. So we get the magnitude of the velocity, because once we reach that constant rotational speed, they said that it was a constant rotation rate. So now we're at, you know, uniform circular motion. So the radius is the 2.5 meters. period is the 1.67 seconds. So what do we get for our speed? How fast was the manual going when they went round and round and round? I assume these are pretty decent numbers, but I could be wrong with that. But usually when they research these, they actually do pretty realistic values. And then, of course, when they make the homework and it randomizes, you get kind of wonky numbers sometimes, but that's all right. There we go. 9.41, 9.40. There it is. Round and round it goes. And then what we can do is we can find our acceleration. We know that that's the v squared over r. We'll take our 9.41 and square it, divide by our 2.5 meters for the radius. So what we get for the magnitude of the acceleration in towards the center. $35.4. There we go. So it's pretty nice. Pretty nice. Yeah, so at normally what they might do is they would go in and divide this by 9.8 to determine how many G's you're pulling on the ride, right? So we're about what, 3 G's, 3 something G's when you divide by the 9.8. So that's always kind of a fun thing they usually do. All right, and so then what we're supposed to figure out is we're supposed to do the diagram. Okay, so this is kind of a top-down view. So it's a view from above looking down. And then what we're going to do is we're going to do a side view. And so here's the wall of the ride. Okay, and then here's going to be our manual. And then they've already dropped the floor down. And this won't really matter, but that's okay. And so when they're going around and around, then they're going to accelerate horizontally in towards the center of the circle. So this is the direction of our centripetal or radial acceleration, like so. And of course, our object of interest is a manual. And so we want to figure out what forces act on our rider. So what do we got? Got gravity. Good. I'm going to go from the center of our person to the center of the earth, so vertically straight down. And then we're like, oh, but they didn't give us the mass of the rider. And the answer to that is we won't need it. So we're going to write it in as m times g, and it should go away in a little bit. So gravity. And yeah, and Emmanuel points out we should have a normal force. Now, which way does the normal force go? Remember the rule? Yeah, yeah. Here's the surface of contact between like Emmanuel's back and the wall, right? And so we're going to go perpendicular to the surface of contact through the object of interest. So if we start at the surface and then go through Emmanuel like this is the direction of the normal force, which is in towards the center of the circle. So really what you get is that normal force is going to produce that centripetal acceleration. And that's kind of cool because normally the normal force is upish, right? And so what other forces do we have? Friction, yes. And so is it static or kinetic friction? I know I read didn't say that. What kind of friction is it going to be and why? I mean, now manual is going around in a circle, but what kind of friction do we have? Static or kinetic? It is static. And how do we know? That is correct. So how do we know? That's the answer I like to see, the one Emmanuel gave. So the bonds between his back and the wall are not breaking. They're not making and breaking as he goes around. He's up against the wall and the bonds stay in place. So really the thing that's holding Emmanuel from sliding down the wall is static friction. And what you get is that the static friction has to be parallel to the surface of contact, so along the wall. And then it goes whichever way we need it to go. And actually, gravity wants Emmanuel to go down to the bottom of the ride, and we want him to stay put. So the static friction's actually going to go up. So this is a very, in my opinion, very interesting force diagram. Yep. Yeah, they're all good. Perfect. So now that we have that figured out, since nothing else is touching Emmanuel, there's just the wall, then you get the normal and the friction. And since he's not sliding along the wall, it's a static. And again, like I said, it's really good because static friction goes whichever way we need it to go so that the bonds don't break. And so we need it to go up to prevent him from sliding down the wall due to the gravitational force. And so then we're going to go in and pick out our coordinate system. And so even though it's vertical and horizontal, you do not want to label this as X and Y. Okay. We want the in towards the center to be the centripetal direction. And then I'll pick the vertical to be Y. Okay. I don't want you to pick X because if we write down AX is just AX, but A centripetal is that V squared over R kind of stuff. And that's what we're going for. Okay. And so then we're going to go in and write down the net force in the Y direction is M times AY. And so I have this plus the static friction minus our gravitational force equals, again, 0 because Emmanuel's not sliding up or down along the wall. And so then when I move this one over, we can actually solve for the amount of static friction that's needed to keep Emmanuel in place as he rides the ride. So that's to equal his weight, so equal to mg. And then when we look in the centripetal direction, we're going to get this net centripetal force is m times a centripetal. Now, again, you got to be careful in the book. Let me remind you that the way they talk about this is as if it's a type. And again, it's not. It's a direction. Okay. Now, the book thankfully uses the radial, so that sounds even less like a type. But the way they really talk about it in the chapter makes it sound like it's a type kind of thing, and it is not a type. It's a direction. The only force we have in that in towards the center of the circle direction is the normal force. So we do plus this normal force is equal to m times plus a centripetal. And so then we put in, this is our normal force is m times v squared over r, like so. Now, again, we don't know the mass, and so we don't know the magnitude of the normal force. We don't know the mass. We don't know the magnitude of the static friction force, but we were supposed to find our coefficient. And so then what we get is that the static friction is less than or equal to mu s times the magnitude of the normal force. And so then I'm going to go in, I'm going to divide both sides by our magnitude of the normal force. Now, since it's a magnitude, it's only positive. And since it's only positive, then I don't have to reverse the direction on the inequality. Right? Because when you multiply or divide across an inequality by a negative, then it reverses the direction of the inequality. Now I'm going to go in, I'm going to rewrite this as mu s. Again, notice that the open is towards the mu, and so I'm going to write it like that so it stays the same. And we'll put our static friction in the numerator, which is this, m times g, and then the normal, which is our m times either v squared over r. We could write that as a centripetal if you want. It's at this stage that you can see that the masses are going to cancel out. So we get g divided by our v squared over r. And I already calculated that here, so I think I'll just leave it like this. that. And so then our mu-s has to be greater than or equal to 9.80 divided by our 35.4. And this gives me 0 point something for our coefficient of friction. .28. There are no units, and that is what we were looking for. Question? Yeah, and it's that funny thing, right? Sachika, Emmanuel is moving around in the circle, but relative to the wall, he didn't go anywhere, right? There's no relative motion between the two surfaces that are in contact. And this is why very often you can end up with, oh, it's moving, it must be kinetic, but then the answer is, well, no, it really wasn't, kind of things. Okay.